Hi, I'm Nathan.
Hi, I'm Bennett.
Hi, I'm Ben.
Hi, I'm Ryan, and this is our roller coaster lab report.
The goal of this lab is to calculate the final speed of the marble at the 100 centimeter mark, which is at the top of the ramp when released from the top. In order to do this, we need to calculate the coefficient of kinetic friction between the marble and the track, which means okay.
In this lab, we assume that the coefficient of kinetic friction between the marble and the track is always constant, although this might not actually be the case since there may be some inconsistency on the surface. We also assume that the second part of the track, past 60 centimeters, is a perfectly circular path for the purpose of using circular motion laws. The rotational kinetic energy of the marble is assumed to not significantly impact the results, but in this lab you'll see that this assumption is one of our main sources of error.
We also assume that the ball navigates the circular part of the path at a somewhat constant speed, which we call velocity average. We did this so that we could find an approximate average value for Fn, since it's constantly changing around the loop.
Our materials are the meter stick, photo gate, protractor, stopwatch, marble, and physics stand. Before we can start any procedure, we first need to set up the scenario. We know the marble starts at the initial height, h1, and ends at the 100 centimeter mark, h final. We also know that some of the gravitational energy is loss of friction, and the rest is converted into kinetic and gravitational energy. So let's set up our conservation of energy equation. First, we have change in energy is equal to 0, and then we have the UGO plus KO equals UGF plus KF plus work of friction. Then MGH1 equals MGH2 plus 1/2 mv squared plus the coefficient of friction times Fn times the distance. The problem is the Fn changes. So first, we need to find the kinetic coefficient of friction.
First, recall that it is easier to find the coefficient of friction on a flat surface. Because Fn doesn't change, like it does in our loop, the calculation is simpler. We know that the coefficient of friction only depends on the types of surfaces it's touching, so the layout of our setup does not affect the value of mu sub k. If the marble is accelerating, this is what the free body diagram looks like.
Using Newton's second law, we can derive that the force in the x direction, just being the kinetic friction force, is directly equal to mass times acceleration. We could rewrite force of friction as coefficient of friction times normal force, which we found using Newton's first law in the y direction. So this means that Fn is directly equal to mass times gravity. Substituting this into the expression for our normal force, we get mu sub k times mg equals ma, which the masses then cancel. So simplifying this further gives us the expression for mu sub k equals average acceleration over gravity.
So we just need to set up a scenario where the marble slows to a stop over a certain distance for a certain time. To do this, we lay the track flat and release the marble from the 62 centimeter mark. We decided to start the stopwatch at the 48 centimeter mark and end it when the marble came to a rest. We recorded the change in distance and the change in time for 5 separate trials. We then calculated each acceleration for the 5 trials from the 45 centimeter mark. We then averaged the acceleration for the average acceleration. This gave us what we needed to solve for mu. In order to find the average acceleration, we use this kinematic equation. So we don't need our initial velocity. We know that it ends at rest. We don't know acceleration, which is what we're finding. We know our delta x and our time from our trials. So using this equation, we can move VFT over to the other side. So we subtract it from both sides, and then we can divide by negative 1/2 t squared, which would give us a equals negative 2 times delta x minus VFT over t squared. But since we know that VF is equal to 0, we know that acceleration is equal to negative 2 delta x over t squared. So coming over here, we can plug that into this equation to find mu sub k, which is just a over g. So once we find our average acceleration, our mu sub k became 0.00456.
Our second procedure is calculating normal force so we can find the work done by friction throughout the whole track.
In order to calculate V final of the marble at the top of the track, we use conservation of mechanical energy. So initially, it starts with potential energy at the top of the track, and this converts into potential energy at the top of the track, kinetic energy at the top of the track, and work done by friction. Okay, after simplifying all the potential energies and kinetic energies, we get mgh1, which is the height at the beginning of the track, mgh2, which is the height at the end of the track, and vf, which is the speed at the end of the track. And we also converted work of friction to mu sub k, fn, and delta x. To get Fn, we took the average of 3 different points on the circular part. First, we took the Fn at the bottom of the track, on the right side of the circle part, and the top part, which is the 100 centimeter mark. So this is the free body diagram for the bottom of the track, where Fg is going down and Fn's going up. And then this is for the right side of the track, where Fn's going to the left and Fg's going down. And this is the top part of the track, where both Fg and Fn are going down. So doing sum of the forces equals m a sub c, because it's following a circular path, we find that Fn is equal to mg plus mb squared over r. And so this is for the bottom of the track. On the right side of the track, we found that Fn is the centripetal force, which is mv squared over r. And then for the top of the track, we found that Fn is equal to mv squared over r minus mg. So taking the average of all these Fn's would result in Fn equals mv squared over r. To get the Fn of the linear part, we drew the free body diagram of the marble on the linear part, and we found out that Fn is equal to mg cosine theta. And so we measured theta using a protractor, and we found that theta equals 48 degrees. So Fn would equal mg cosine of 48 degrees. So in order to get the total Fn of the entire track, we took the weighted average of the circular part and the linear part. To do this, we know that 40% of the track is the circular part, so this is why we multiply by 0.4. And we know that the linear part is 60% of the track, this is why we multiply by 0.6. So the circular part, we found that Fn was mb squared over r. And so we multiplied that by 0.4, and we know that the linear Fn is mg cosine theta, so this is why we multiply by 0.6, which would give us the total Fn, which we would put into this equation in order to find Vf.
After plugging in our numbers and isolating Vf, we found that Vf equals 2.239 meters per second. Our observed value for the final velocity at the top of the loop is 1.711 meters per second. Using this formula to find the percent error, we found that our error percent is 30.8%.
At the conclusion of our lab, we determined the value of the coefficient of kinetic friction to be 0.00456. We calculated the coefficient by experimenting with the marble on the track laid down horizontally, collecting data for the time and displacement for all 5 trials. We only needed to find displacement over time to solve for acceleration, since the final velocity in this scenario was known. Then, using Newton's laws, we equated the coefficient of kinetic friction to be the average acceleration divided by g. To calculate the velocity at the top of the loop, we found that it was necessary to find the coefficient of kinetic friction and the normal force once we set up the conservation of energy equation.
So we calculated our Vf final to be 2.239 meters per second, but our actual V final was 1.711 meters per second. So this gave us a 30.8% error. This can be attributed to not accounting for Ke rotational. When the ball rolls, part of this initial potential energy is converted into rotational energy, which takes away from the linear kinetic energy that supplies the speed. Our solution didn't account for rotational kinetic energy, and if it had, our velocity would have been closer to the actual velocity, since Kr reduces linear velocity.
Our second source of error comes from the roughness of the track. In our lab, we assumed that the friction on the track was the same throughout. It is the small discrepancies in the loop that make the marble lose the most of its kinetic energy. The problem doesn't come from the friction, but from the unevenness of the track. It's comparable to running over large rocks on the road while driving. There's too much structural interference on the track. It's not as much about the texture of the surface. Despite this, our calculated value of the coefficient of kinetic friction was extremely small, almost negligible.
Finding the ideal work of friction in the lab doesn't really help us find the actual velocity. It is ideal work of friction when we calculate the work of friction from formulas and not from actual measurable means. In reality, there are more external forces than work of friction that cause the velocity to be much lower than expected, such as rotational energy. Had we calculated work of friction as a whole via measurable means, such as calculating the ideal time for the marble to roll down the track, and record the real time, and calculate the real velocity based on proportional reasoning, we would have been much closer to the actual velocity, because this means would treat work of friction as another way of saying loss and energy. For example, if the time down the ramp was recorded to be 5 seconds, and the ideal time is 3 seconds, then the difference is accounted for in the loss of energy.
Thank you for watching.